Okay, so today's video is going to be about drawing Lewis structures using the electrons needed, electrons have method, which is the method that we discussed in class. So what we want to remember is what a Lewis structure actually tells us about the molecule. We need to have the correct Lewis structure to figure out the overall shape of the molecule, because that's going to tell us eventually about molecular geometry and molecular polarity. But when you draw a Lewis structure, dots are going to represent electrons or lone pairs, and lines are going to represent a bond. Remember that every one line is 2 electrons. So if there are 2 lines, it's 4 electrons being shared, or a double covalent bond. And if there are 3 lines between 2 atoms, that would be a triple covalent bond, or 6 electrons total being shared. Okay, so the steps that we're going to use in this technique is the first thing we need to do is calculate how many valence electrons each atom in the molecule would want if it was a noble gas by itself. Now we know that these atoms are not actually going to be by themselves. They've entered into this covalent bond in order to get what they need, but this is to help us figure out how many bonds we need to actually draw for our molecule. It's very important to remember what the exceptions are. The exceptions to the rule are going to deal with hydrogen and helium and lithium and beryllium and boron, and you have those in your notes in terms of what electrons they need. The second thing you want to do is to calculate the actual number of valence electrons each atom in the molecule has. We use that by looking at the group A number. Then we're going to subtract. That will tell us how many electrons are being shared, and keeping in mind that every shared electron is being shared between 2 atoms, we divide it in half, and that will tell us the number of bonds formed. The last thing we want to keep in mind is about the central atom. The central atom is typically the least electronegative because it's going to be sharing its electrons with lots of other atoms. Or if you have a formula written and there's only one of an atom, it typically is going to be that atom that goes in the center. One thing we want to remember is that even though oftentimes there's only one hydrogen written, hydrogen can never be in a center because once it is in one bond, it's not going to bond anymore. So you can't bond more than one single bond of hydrogen, so that makes it not a good candidate for being the central molecule. Okay, so let's take a look at 2 examples. The first one that we're going to look at is CH4. So when we look at CH4, we want to start thinking about how many electrons they would need if each of these elements were a noble gas by themselves. If you're looking at your periodic table and you look at carbon, carbon's nearest noble gas is going to be neon, and neon has 8 valence electrons by itself. Hydrogen, on the other hand, its nearest noble gas is going to be helium, and each helium needs 2 valence electrons in order to fill its 1s orbital. So when we're thinking about how many CH4 is going to need, the carbon would need 8, and each of the hydrogens would need 2. So that's 8 plus 4 times 2, and excuse the writing here. 8 plus 4 times 2, so 4 times 2 is going to be 8, plus 8 is going to give us 16. Now that would be 16 electrons if we drew each of these atoms individually, so the carbon separate and our 4 hydrogens separate. But in reality, they're not separate. They are here together in a bond so that they can get to noble gas configuration using just what they have. So if we go back and think about what they have, and you look at the periodic table, carbon is going to have 4 valence electrons because it's in group 4A. Hydrogen is going to have 1 valence electron each because it's in group 1A. So that means that they actually have 4 plus, and I'm just going to say 4 to represent 4 times 1 because it's easier to write. So 4 plus 4 means that they actually have 8. So we've got 8 valence electrons, but we would actually need a total of 16 if they were all going to be by themselves. Well, they're not all by themselves, so what we do next is we're going to subtract. 16 minus 8 means that we have 8 electrons that are shared in bonds. Remembering that every bond contains 2 electrons, 8 divided by 2 means that we actually have 4 bonds. So you might think that this is pretty easy to figure out because we have 4 hydrogens and 1 carbon. We are in fact going to put our carbon in the center. You can't put hydrogen on. We're going to branch off our 4 hydrogens. Here's 1, And then here's another one, 2, 3, and 4. And that's going to give us all the electrons that are in a bond. And if we take a minute and look, if you look at just this hydrogen here, it has access to 2 valence electrons, which are shared in the bond. So it is now at a noble gas electron configuration. And if we look at carbon, which has access to all of these in the middle, it has 8. So we do not need to draw any lone pairs on. This structure is going to be done. If we look at another example, something that's a little bit more complicated, we're going to look at phosphite, which is a polyatomic ion. So what that means is that this group of atoms are sharing electrons, but they have also needed to gain electrons in order to get to noble gas configuration for all of those elements. It doesn't really change much of how we do this, except for we're going to make a small addition in the electrons that they have to share. So let's go back and think about what they would need. Both phosphorus and oxygen would need 8 valence electrons if they were going to be by themselves. So if we think that there is a 1 here, there's 1 phosphorus and 3 oxygens, that's 4 total atoms. Well, 4 times 8 is going to be 32, so they would need 32 electrons to be all by themselves. So now let's take a look at what they have. Phosphorus in reality is in group 5, so it has 5. And oxygen is in group 6A, so it's going to have 6. So 3 times 6 is going to be 18. 18 plus the 5 is going to be 23. And then we have this -3 to deal with. So -3 means that it has gained 3 electrons. So 23 plus 3 is going to bring our total to 26. So what this is going to allow us to do, again, is when you look at the difference or you subtract it, you'll be able to tell that there are 6 electrons being shared, or there are 6 electrons that are being shared in 3 bonds. Again, we're getting that by 6 divided by 2. Now in this situation, we would want to put our phosphorus in the center. It's our single atom, and we have 3 other oxygens that we're going to connect. So we're going to connect them with single bonds. So here's 1. You know how I like to draw my O's. Here's 2. And here's our 3rd one here. Now we're not quite done with this structure, unlike the last one, because none of the elements here have reached noble gas configuration. All we've done so far is we've put in our 3 bonds, so we have to go back and look at each of these. Now all of our oxygens look identical, so we can just evaluate them once. And when we look at this oxygen, right now it has access to 2 valence electrons, but its noble gas has 8, so we're going to put 1, 2, 3, 4, 5, 6 back on our oxygen so that it has 8. All of these oxygens look identical in their bonds, so everybody is going to need 6. And then we're going to look at the phosphorus in the center. Remember that shared electrons, or electrons shared in bonds, count twice, and that the phosphorus can access them and also the oxygen can access them. So if we look at the phosphorus, right now it has access to 6, so we need to put 2 more valence electrons, or a lone pair, onto phosphorus, so that phosphorus has an octet. And you can check your work by counting the number, and if you check, there's 26 electrons used, and we need to indicate that this is a polyatomic ion, so we're going to put a bracket around the charge, and this is going to have a charge of -3. Okay, so that should finish up that ion. We're going to do one more, and this time we're going to look at SiO2, or we're going to look at silicon dioxide. Again, we're going to use this technique of electrons needed versus what they have. So if we look at each of these elements, both silicon and oxygen, their noble gases are going to have 8 valence electrons. And if they have 8 valence electrons and we've got 3 atoms, then to be individual atoms without entering into a bond, we would need a total of 24 electrons. Comparing to what they have, since silicon is in group 4, it has 4 electrons. Oxygen is in group 6, so it has 6. So 2 times 6 is going to be 12. plus the 4 from silicon means that they actually have 16. So if we do the subtraction, 24 minus 16 means that we have 8 electrons that are being shared. We divide that in half, which means that we've got 4 bonds. When we're looking for our central atom here, we want to pick silicon because it needs the most to get to noble gas configuration, so we're going to put silicon in the center. When we put silicon in the center, and we branch our oxygens off, we have 2 oxygens, so here's one and here's the other. We still have to use 2 more bonds, and this is the strength of this method. Instead of trying to draw and erase and figure out how many bonds you would need, you know you need 4 bonds. So if you need 4 bonds, you're going to put 2 on each side, because again, in chemistry, what we see is that symmetrical is typically what you're going to find in nature. So then if we look at this silicon, we do not want to add any more valence electrons, and this is the I from the silicon. It is not a valence electron. If we look at the oxygens, however, oxygen right now has access to 4 shared electrons, so we need to draw 2 lone pairs or 4 more electrons on each of our oxygen. If we count the total number of electrons that we have used 2, 4, 6, 8, 10, 12, 14, 16, so this has 2 double bonds. Something else that we want to remember about double bonds is double bonds are stronger than single covalent bonds because they actually draw the atoms closer together, meaning it takes more energy in order to break them apart. Okay, and tomorrow in class we're going to talk about exceptions to the general octet rule, but this should give you a good start for tonight.